Okay, so this class CS161, it has a few different kind of really central purposes, and one of them is you'll be exposed to a lot of fundamental computational problems where it's not necessarily obvious how to solve them, but they can in fact not just be solved, but be solved super quickly. So linear time or very close to linear time. Okay, so one thing you'll take out of this class is sort of a toolbox of primitives, of subroutines, which maybe aren't sort of the problem you want to solve in its own right, but are sort of a for-free pre-processing subroutine. So maybe the canonical such subroutine would be sorting, but if you have an array, maybe you're not even sure yet whether you care if it's sorted or not, but you wouldn't think twice about invoking a sorting routine on it, because it just works so blazingly fast. I'm talking about, for the moment, I'm talking about data sets which fit in main memory, which is a lot of the data sets you'll come across, not necessarily all of them. If you're working on the web graph or something like that, obviously that's not going to fit in the main memory of your personal computer. But for anything which fits in main memory of your machine, a near linear time subroutine, you should almost just think of use it even if you don't know why. Okay, just because it's for free. All right. So we've seen a couple of those so far, and the theme of this week is we're going to discuss a few of these for-free or near linear time primitives for graphs, operations on graphs. Okay? And so I'll show you 3 or 4 of these today, and then another more complex one on Thursday, most of which have the flavor of graph search. In addition, talking about some of these graph algorithms will be a natural segue into our discussion of greedy algorithms, which will be our second main algorithm design paradigm. We'll see a sort of example of that today in DIJKSTRA'S algorithm, and then we'll talk about greedy algorithms in earnest next week. Okay? So first, just a few points of review, which you've probably seen before, but let me just do a blazing fast review. So first of all, how would you actually represent a graph, a bunch of vertices or nodes, and a bunch of edges as a data structure? Well, there's a couple ways to do it. Okay, so some standard notation. G will be a graph, V is the vertices, or I'll also call them nodes. E is the edges. And unlike arrays, there's more than one input parameter. Okay, so we're often used to thinking about a problem just having some size n. One thing about graphs is there's really 2 different measures of how big they are, the number of nodes and the number of edges. And the notation we'll always be using is n will be the number of vertices, and m will be the number of edges. Okay? And for the moment, I'll relax this in a couple of weeks. But for the moment, we're going to think about so-called simple graphs. So for the moment, we won't worry about parallel edges, meaning you have 2 nodes and 2 edges, or 2 edges going in the same direction. Okay, so parallel edges won't be relevant for the next several lectures. Okay, so just assume that they're not there. All right? So there's some basic rules. So we do have these 2 different measures of how big a graph is, but there are some simple relationships between them. So suppose we have an undirected graph. We'll be talking about both undirected and directed graphs this week. So suppose edges have no directions, and there's no parallel edges. How large could m be, the number of edges, as a function of n, the number of vertices? Yeah, m choose 2. Right, so the densest possible graph would be fully filled in. It's called a clique. And for each of the pairs of vertices, there would be an edge. Okay? So that's the biggest it could get. How about if G is directed? Well, there are twice as many, right? Because for each edge in the undirected version, you could have an arc directed either direction. Okay, and that would still avoid parallel edges. So that's n times n minus 1. But in any case, the number of edges with no parallel edges is always going to be O of n squared. Okay? So that's as big as n could be in terms of n. In particular, I want you to notice that if we take logs, and this is just a notational convention I'm introducing you to, log m is big O of log n. Okay? And I'm just warning you now, we're going to be very sloppy. If something's inside of a big O, we're not going to really distinguish between whether it's log m or log n. Okay? And so usually we'll write log n. That's the convention, even if sort of log m is kind of more directly what we mean. All right? So get used to seeing this, not this, inside of the big O notation. All right? So how small could m be? Well, on the one hand, m could be 0, right? You could have a bunch of vertices in an empty graph. That's not that interesting. But for most of the graphs that we talk about, we're going to think of graphs that are in one piece, that are connected in some sense. And so maybe just for this question, think about an undirected graph for simplicity. So if G is connected, and we'll talk more about what that means later today, but I think you know intuitively what I mean. How many edges does it have to have? Yeah. n minus 1. That's right. Okay, and again, if you haven't seen, probably you've all seen that before in 103. If you haven't, we'll talk more about that later. But the point is, for a connected graph, n has got to be omega of n, at least basically n. So usually, not always, but usually when we talk about graphs, we do have these two different parameters, n and m, but m will only vary somewhere between linear in the number of nodes, n, that would be a sparse graph, and quadratic, n squared, which would be a dense graph. Okay? So that's some feel for these parameters m and n.